Lesson 67. In this lesson, we'll be looking at related rates problems involving trig derivatives. Here is example 1. A balloon leaves the ground 500 meters away from an observer and rises vertically at the rate of 140 meters per minute. At what rate is the angle of elevation of the observer's line of sight increasing at the instant when the balloon is exactly 500 meters above ground? If you recall how we dealt with related rates problems, in most cases we started with a diagram. So here we go. Let me find my straight lines. So let's draw the ground and then the path of the balloon. We know that the balloon is increasing from a certain height to a higher height. Let's put some labels on this diagram. We'll use red. It leaves the ground 500 meters away from an observer. So I know that the distance between the observer and the balloon from the ground side is 500 meters. And then it's rising, so it's going up. Let's call this dy by dt at a rate of 140 meters per minute. Okay. We are interested in a rate relating to the angle. That means this is d theta by dt at the instant when the balloon is exactly 500 meters above the ground. So let's say it reaches a height of 500 at this moment. Okay. These are all the given information, and we have put them on the diagram. Now we need to set up an equation to relate theta and also the height of the balloon. Since we're dealing with a horizontal and a vertical distance, naturally we can consider using tangent theta equals to y over the horizontal distance, which is always constant at 500 meters. We know that the next step is to get the rates of change involved. Let's take the derivative of both sides of this equation. We have secant squared theta d theta dt equals 1 over 500 as a coefficient. And now we need to take the derivative of y with respect to time. It is simply 1 times dy by dt. And then we know that when the height y is 500 meters, the x direction is still 500 meters, which implies that the angle between the line of sight and the ground must be pi over 4 because this is an isosceles right triangle. Using these information, we substitute into secant squared theta is now pi over 4 times d theta dt equals 1 over 500 times dy by dt, and we know that this is 140 meters per minute. Let's solve for d theta dt equals. So on the right side, I have 14 over 50. And then I need to divide by secant squared pi over 4. But this is the same as cosine squared of pi over 4. This is 7 over 25 times root 2 over 2 squared, which means that d theta by dt is equal to 7 over 50. And the units that we are using is radians per minute. Here is example 2. A ladder 4 meters long is leaning against the side of a building. If the foot of the ladder is pulled away from the building at a rate of 3 centimeters per second, how fast is the angle formed by the ladder and the ground changing at the instant when the top of the letter is 3 meters above the ground. So we have done similar questions before, but that was relating the length of the 3 sides of a right triangle in a sense. So we have changing this, and we're interested in looking at the rate of change of angles. Let's start with the diagram. So here's the wall and the ground, and here's the letter. Let me make it a little longer. That's better. Nope, that's not good. That's better now. All right, so let's put our labels on this diagram again. The letter itself is 4 meters long. The foot of the letter is being pulled away from the building, so going to the right, assuming, and at the rate of 3 centimeters per second. So let's call this dx by dt. How fast is the angle formed by the letter and the ground changing? So we're looking at d theta by dt if this angle is theta. Okay. And when the top of the letter is 3 meters above the ground. So this part is 3 meters. Okay. Notice how the rate of change in the horizontal direction is in centimeters, but the length of the letter and the position above the wall are in meters. So don't forget that we have to use consistent units. Let's change this into 0.03 meters per second. I know that this is going to involve theta, the opposite side, and also the hypotenuse. But I also know that my given rate of change is related to the adjacent side. So how am I going to pick my trig ratio to reflect all the unknowns and given variables? It actually looks like cosine theta is a better choice, because then I can relate d theta by dt to dx by dt. So let's write this out. Cos theta is the x direction over hypotenuse, which means when I differentiate this, I get negative sine theta d theta by dt equals 1 over 4 dx by dt. Do I have all the information that I need? Well, I would have to know what theta is when the letter is 3 meters above ground, which means that I'm interested in arc sine of 3/4. So I'm taking negative sine of arc sine 3/4 d theta dt equals 1 over 4 times 0.03. Solving for d theta dt, I get negative 0.01, because sine of arc sine 3 over 4 is really 3 over 4, so we have negative 3 over 4 on the left, and then when I divide that from the right side, that's what I'll get. And this is describing how the angle is actually decreasing, because as the letter falls, theta will become smaller and smaller and smaller. And this is in radians per seconds.